Pop quiz. As a hot cup of coffee cools in a room, what happens to the entropy of the universe? It decreases, increases, or stays the same? Lock in your answer. We'll come back to it soon. In this video, you'll learn what entropy really means and what the second law of thermodynamics tells us. You'll see how to view the universe as a system and its surroundings, how to recognize spontaneous processes, and how to avoid common myths about entropy. In the 1800s, engineers realized something surprising. Heat always flows from hot to cold, and no engine can ever be perfectly efficient. That insight led to the idea of entropy and the second law of thermodynamics. Entropy describes how energy spreads out or becomes more evenly distributed. When heat enters a system, entropy increases. When heat leaves, it decreases. To apply the second law, imagine the universe as two parts, the system we study and its surroundings. Each can gain or lose entropy as energy moves between them. In natural, spontaneous processes, energy spreads out on its own, and the universe's total entropy increases. Now, let's return to the quiz question. As coffee cools, heat leaves the cup and warms the surrounding air. The coffee's entropy decreases, but the room's increases slightly more, so the universe's total entropy rises. Cooling is spontaneous. So far, we've learned what entropy means, how to view the universe as a system and its surroundings, and how to tell when a process is spontaneous. Take a moment to review these ideas before we connect entropy to microscopic possibilities. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide. Then jump right back into the video. Lock in what you learned and keep going. Let's look at another example. A snowflake melts in air just above freezing. The system's entropy rises as an ordered solid becomes a freer liquid. The surroundings lose a little heat and entropy, but the system's gain is larger. Melting is spontaneous above the melting point. At equilibrium, when melting and freezing coexist at 0 degrees, the total entropy change of the universe is 0. Neither direction is favored. Both happen at the same rate. The system's entropy can still change. It's the total that matters. Here's a quick myth fix. Entropy isn't simply a measure of disorder. It's about how many microscopic arrangements are possible. The more ways energy and particles can be arranged, the higher the entropy, even when things still look orderly. Now, let's apply that idea to a twist. Dissolving ammonium nitrate feels cold. Heat moves from the air into the solution, so the surroundings lose entropy. But the particles in the mixture gain far more possible arrangements, increasing the system's entropy. Overall, the total still rises. The process is spontaneous. Now, let's recap what we've learned. The second law links spontaneity to an overall increase in entropy. Entropy measures how energy and matter can spread among microscopic arrangements. More possibilities mean higher entropy. At equilibrium, the total change is 0, and nature finds its balance. Now that you've watched the video, let's see how much you remember. Head to the link in the description, where you'll find Quizlet content made just for you.